Yes, so the last talk, we conclude this session by
flapping wing couple dynamics in the group setting.
From University of Zagreb.
This is the outline of my talk. First, I will be talking on motivation. First part. This is the outline of my talk. First, I will be talking on motivation. First part is devoted to design aspects. Why should we design flapping wings at all? Then, I will focus on the mathematical part, giving you a motivation of adopting geometric approach for modeling, mathematical and mechanical modeling of our systems. After exposing few fundamental issues on solid fluid geometric mechanics, I will proceed with multi-body fluid system coupled formulation, and in the end I will provide a few examples. So, why should we design flapping fly systems? As we all know, rotary wing technology is prevailing technology today in the context of UAVs, unmanned aerial vehicles, so-called drones. However, if we scale down the geometry of such a vehicle in order to design small aircraft, we enter the realm of low Reynolds number flight regime. And in such a regime, aerodynamics of rotary wing deteriorates significantly. If we take a look in this diagram showing lift to drag ratio, we see that in the domain of low Reynolds numbers, this ratio is much worse comparing to domain of Reynolds numbers of conventional aircraft, meaning that rotary wing technology is not the best option for flying at low Reynolds numbers. However, there is an alternative. Evolution for flying at such low Reynolds numbers came up with a flapping flight. Here we see a fossil of a flapping wing from 350 million years ago, meaning that flapping flight is not a new invention. Here on these diagrams we see further proofs that flapping wing is more energy efficient than revolving rotary wing for flying at low Reynolds numbers. We achieve better lift, higher lift, and we consume less power. On this diagram, we see a relation between a mean thrust and power, and here we see that flapping wing also performs better comparing to various different variants of rotary wings. According to some investigations, flapping wing propulsion under the drive of the same motor can be up to 40% more energy efficient than propulsion with rotating propellers. However, it's not only energy efficiency that provides motivation for flapping flight design. Flapping flight can provide outstanding aerial capabilities for flying backwards, sideways, hovering, etc. Also, we can have a structural robustness of such a design and excellent adaptability on various different environmental changes. Let's proceed with the second part of our motivational section. In order to model physics of flapping wing, we have adopted geometric mechanics approach. Why did we choose so? Beside the fact that there is a traditional link between analytical mechanics and differential geometry, two important issues in the context of multi-body system dynamics, being modeling of finite rotations and numerical treatment of configuration constraints, call naturally for geometric mathematical framework. Beside that, geometric framework allows for designing of structure-preserving numerical integration schemes that respect underlying kinematic and dynamic structure of the system. However, probably most important issue is that geometric framework gives a possibility of exploitation of system symmetries and design of reduced order models that gives a direct link toward learning algorithms on manifolds and Lie group machine learning. Design of reduced order models gives us possibility to come up with much more efficient computational procedures. Standard way of coupling fluid and solid dynamics is to use different solvers for a fluid domain and for a solid dynamics. Then we try to find a right method to get these guys to talk to each other. However, if we have large motions on a solid side, this means that we should probably use moving meshes for solving fluid dynamics, and this could give problems with accuracy, stability, etc. Also, there are situations when we are mostly interested in a solid motion and how fluid influences solid dynamics. This means that we are not that much interested in specifics of a fluid motion, and in that case it would be a real advantage if we could reduce out fluid variables and solve couple problem by using solid variables at the first place. There is a question if we could do so. Yes, we can, and this is the point where geometric mechanics come into play. Because from geometric framework, rigid body and ideal incompressible fluid have analogy in mathematical structure, being that configuration space of both objects are Lie groups. Special Euclidean group in the context of rigid body, or direct product between rotation group and translations, and in the context of incompressible fluid, we have volume-preserving diffeomorphism. In both cases, we are completely equipped to deal with 3D dynamics. However, sometimes 2D approach has its benefits, and we will use both approaches in this presentation. Volume-preserving diffeomorphism represents position field of the fluid particles. We have two approaches. We have Lagrangian and Eulerian approach. However, only Eulerian approach gives a real velocity field of the fluid particles. Also, there is a right invariance of Eulerian description regarding particle relabeling symmetry. This means that Eulerian velocity field will not be changed if we bring a new set of particles at the reference position before the process. In both cases, at the identity of the groups, velocities live in Lie algebras. In the context of rigid body, if configuration space is expressed as direct product of SO3 rotation group and translations, angular velocity of the body lives in Lie algebra, SO3. In the context of incompressible fluid, we have divergence-free vector fields tangent to the boundary. We also need to introduce dual spaces of Lie algebras. In the context of rigid body, element of dual space of Lie algebra is angular momentum, and for incompressible fluid, we have vorticity or circulation. Let's introduce symmetry that we will be using in our reduced order modeling. We have already introduced right invariance of Eulerian description for fluid. This means that kinetic energy of fluid will not be changed if we act from the right with volume-preserving diffeomorphism Lie group. In the context of rigid body, we have a left invariant velocity field. If we focus on the rotational part of rigid body motion, kinetic energy of body will not be changed if we act with SO3 Lie group from the left. According to Noether theorem, if Hamiltonian of the system is invariant on Lie group action, pertinent momentum map is conserved. In the context of rigid body rotational motion, momentum map associated SO3 Lie group is angular momentum that lives in dual space of Lie algebra. If kinetic energy of rotational part of rigid body motion or Lagrangian of such a motion is invariant on this Lie group action from the left, then angular momentum will be conserved, or, speaking language of geometric mechanics, quadjoint orbits will be preserved. This fact can be used for designing of structure-preserving integration scheme for rotational part of free rigid body motion. In that case, if we write down Euler equation in so-called Lie-Poisson form, we can seek for a solution in this form, meaning that we only rotate angular momentum vector during rigid body rotational motion, meaning that integration point of this process will always lie on the sphere. For the fluid side, momentum map associated with volume-preserving diffeomorphism is vorticity or circulation, that, as we have already seen, live also in dual space of fluid Lie algebra. If fluid kinetic energy is diff-wall invariant, of course, this also means that quadrant orbits will be preserved, giving rise to Kelvin's theorem that states that circulation around closed curve is preserved or vorticity is advected. For coupled problem modeling, we assume system consisting of k bodies and fluid that occupies region M in 2- or 3-dimensional Euclidean space. This means that configuration space of coupled system is set of all appropriate maps from M to M. We assume potential flow with no vorticity, which means that fluid velocity can be expressed via potential or solved by using Laplacian equation. Later, we will relax no vorticity assumption, meaning that according to Helmholtz-Hodge decomposition theorem, we will add divergence-free velocity field coming from a circulatory flow to already existing Laplacian flow. Now, we will apply particle relabeling symmetry to the coupled problem. In the same way, like in the context of rigid body rotational motion, Lie-Poisson reduction reduces out rotational variables because SO3 group acting from the left act on them. Volume-preserving diffeomorphism acting from the right on the coupled problem reduces out fluid displacements. Since we have assumed zero circulation, the whole coupled problem can be now expressed only via rigid body variables consisting of rigid body displacements and angular momenta. However, in this rigid body angular momenta, now we have incorporated added mass effect, which encodes influence of ambiental fluid to rigid body motion. What we have just described is symplectic reduction at zero level of circulation that eliminates fluid variables out of the picture. This also means that reduced Lagrangian of fluid multibody system is function of rigid body variables only, and effect of fluid to rigid body motion is encoded only through added mass or added inertia effect. As we have already seen, particle relabeling symmetry gives rise to Kelvin's theorem, saying that circulation that is assumed to be zero here is preserved. Since, as we have seen, velocity for this kind of flow can be determined from velocity potential, calculation of added inertias is based on solving of Laplace equation for Neumann boundary conditions. However, solving of Laplace equation can be replaced by easier boundary value problem, which can be numerically solved via boundary element method. With this procedure, we have replaced necessity of whole fluid domain discretization with much more efficient boundary surface discretization. Dynamics of coupled problem consisting of k bodies immersed in ideal ambient fluid is now described by means of immersed multi-body state space variables only, consisting of position and rotation of each body, as well as velocity and angular velocity of each body. Now, equations of dynamics of immersed multi-body system in ambient fluid can be expressed in the same form like dynamics of multi-body system moving in a vacuum, with the only difference that added mass effect should now be incorporated in the system inertia matrix. Also, on the right-hand side, we should include terms of extended Kirchhoff equations. Later on, we will also include forces coming from circulatory part of fluid flow. Since we live in a Lie group, Monte Carlo type of integration algorithm can be used to solve dynamics of the coupled problem. On next few slides, simulation results of multi-body system moving in fluid flow without circulation are presented. Depicted curves are curves of fluid flow velocity potential. In order to formulate reduced order model for rigid body moving in the fluid flow with circulation, we should go back to symplectic reduction we have introduced before. However, now we won't have a reduction at zero level of vorticity, but contingent bundle reduction at certain level of circulation momentum up. However, since default Lie group is full symmetry group, we can establish the same isomorphism as before, meaning that we can reduce out fluid variables and establish the whole dynamics of Laplacian flow by only using rigid body variables. In angular momentum, we will have encoded added mass as before. It can be shown that manifold of a coupled problem is principal bundle over group of rigid body motion, and Neumann connection can be established whose curvature generates Kutta-Zhukovsky force that should be included as additional force in our dynamical model. On last slide, we had formulated equations of coupled model reduced at certain level of circulation. However, since we have unsteady flow, circulation is changing all the time. Therefore, we should introduce vortex shading mechanism. This mechanism can be enforced by Kutta condition that states that velocity at the sharp edge must have meaningful physical value. To this end, several authors propose different algorithms to enforce Kutta condition. However, in most of the cases, position of the next shed vortex is not determined exactly, but it is assumed at a certain position. Here we see vortex shedding mechanism from the body moving in aqua fluid. In order to calculate circulatory forces, in our approach we adopt unsteady potential flow discrete vortex method. Since leading edge vortices are very important for flapping wing dynamics, we also incorporate shedding mechanism for leading edge vortices. To estimate shedding points, we adopt experimentally obtained fact that for optimal propulsive efficiency, through Hall number of the flow should be kept at fixed range. This fact can be used for calculation of shedding points. On this slide, we see circulatory flow of two flapping wing simulation cases. Here we have only trailing edge vortices considered, and on this slide we have both leading edge vortices and trailing edge vortices presented. Thank you for your attention.
Oh, sorry, Zlatar, you are connected.
Sorry?
Yes, we are late, so we have no time for question. So I invite attendees to send you email if they are interested. For your information, I send all your papers to Onera in France.
Okay.
That are working on wake vortex. And I think it's a very interesting job and very impressive result. Thank you for your presentation on your model. Thank you.
Thank you very much, Frederic.
We will switch to the last session.
Yeah.
C'est vous qui commence.
Eric,
I introduce Frederic Zarvaresco, who is presenting the first talk.
Okay, so it's hard at the end of the day. You are exhausted. You don't know where you are, what is your name, and you don't know what is entropy. Or you are forget. So I would like to motivate you to read Suryo, to have a new definition of entropy. I think it is a new definition. Or a new characterization of entropy, which is entropy as an invariant Casimir function in coadjoint representation.